Hi everyone, we'll start in about 1 to 2 minutes time. Alright, good afternoon everyone, and today's lectures are going to be on the impulse response and system characteristics in particular. The first lecture here is going to be based on the impulse response, but we'll be doing a short recap as to why we are focusing on certain things in this course in the start of this lecture. And then the second lecture will be focusing on system characteristics and how can you characterize systems by certain terms and whatnot. And we'll learn like what those terminologies would be, as well as how do we identify when those terms occur for us to define our systems accordingly. So at this point we might want to take a little bit of a reality check, and we want to ask, well, what's the purpose of doing signals and systems? And in particular, because the entire engineering field is applied science, you're basically going to be dealing with some sort of input signal and process output signal, and in order to obtain this process output signal, it means that the input signal must be subjected to some sort of system. And this system is designed by certain requirements, in order to produce the required output signal that is expected. So the purpose of this course is basically to figure out how the system will respond to a signal that it will be likely subjected to, and how we can design systems accordingly to get our required output signals from our obtained input signals. One thing to note though is that even though we are watching this from a theoretical aspect, in a real life design situation, you can't really predict all the time what sort of input signals you want to be getting. So as of such, you will have to factor in some design considerations as to how would you mitigate unwanted signals within your system and so forth, and how would you deal with unexpected inputs and whatnot. But we'll talk about that later on within the course itself. But for now, we'll be looking towards more of the ideal scenarios themselves. So typically what is known for our signals would be that we know some sort of limits will exist, some speed response and some range response. And in particular for the limits, we will know what would be the signal amplitude and the signal frequency. The speed of response would be how fast will our system respond to our input signals. And the range of response would be basically what could be the range of our output in this particular case. So let's say we have a frequency range that is acceptable for a bandpass filter. That basically is going to be the range of response for our system in that particular case. So in particular, for people who did the BGT project in Lab and Project Design 1 last year, from the knowledge that you know from the first 4 lectures at this point in time, you actually can apply some of this knowledge into your BGT project to figure out, okay, how do I characterize the properties of our BGT amplifier in particular? So those properties would be the gain of the amplifier, the frequency response of the amplifier, as well as things like maximum symmetrical swing, which is a characteristic of it, that is also defined by the signal amplitude and also the signal frequency. So certain things that in particular that you did in the BGT project, it will be more applicable at this point in time, since you will be getting the knowledge as to how you can define your systems and so forth. And this knowledge in particular will be useful for defining any signals and any systems going forth throughout the entire degree. So in dealing with signals and systems in particular, we need to ask what could be done possibly from what is known, and what can actually be done in some cases where we have unknown conditions and so forth. So before we start designing our system, we can basically have an idea of what our input signals are going to be beforehand. And we can determine that range beforehand for what we are expecting and what we may not expect as well. So we can say, okay, we want to accept signals with an amplitude higher than a certain value or lower than a certain value or within a certain range, as well as we want signals to be higher than a certain frequency, lower than a certain frequency, and within a certain range of frequencies and so forth. In some cases, we can't really know all the time what the input signals are going to be, but we'll have some general idea of what they can be. So as of such, the shape of the input signals may not be known in this case. And if it's not known, you actually have to use substitute signals to test your system design to get an idea, okay, how would your system respond to certain types of signals? And those standard signals will be the signals that we saw in yesterday's lecture in particular, and last week's lecture as well, which would be the 4 general signals, which will be the impulse, the step, the sine, and the ramp signals in particular. These 4 signals are very useful in testing your system. And you'll see why later on, why the impulse and the step response in particular is going to be very useful for testing the response of your system. So in general, because we have these standard signals and we can subject it to our design system, this basically allows us to predict how the system should respond to general real-world signals. And the 2 tests that we typically always use for testing any type of systems will be the step response and the impulse response. And you will see why later on when we start defining these signals within time and then we move towards frequency, as to why these signals characteristics are so important for rigorous testing of systems in particular. Especially when you go on into power systems, communications, and control systems in particular. These 2 tests are very important for determining and troubleshooting problems within your system itself. So let's actually watch one of these signals and how it actually can respond to a simple circuit design and what is important about it in particular. So we have a standard resistor capacitor circuit here, or RC circuit, and basically we know that it's possible for us to find a y of t equation to figure out what is going to be the initial charge of the capacitor and so forth, and how can we obtain our output equation accordingly. And the question that's going to be asked here is what's going to be the response of the circuit when the circuit is actually switched on at time equals 0. So if you can recall from ECNG 1016, it was possible to actually formulate a differential equation from that actual circuit based on all its RC components and input and output signals, where x of t will be the input signal and y of t will be an output signal, y of t being the voltage across the capacitor in this particular case. And in order to solve this, we could either do time differential analysis, which was very long, but because we're engineers, we basically use the Laplace transform to shorten our work quite considerably, and we will obtain an equation in terms of Laplace. In this case, we will obtain a y of s equation. And because we're dealing with the Laplace transform, it's also possible to do the inverse Laplace transform to get it back in terms of the time domain. Now, because, well, I have to go back one slide. So in particular, since we have our outputs here map on the left hand side and our inputs here map on the right hand side, the initial question asks what's going to be the step response in particular and what we will observe in respect to the step response. So the step response is basically literally like when the circuit is switched on, because it goes from 0 to some predetermined value, which in this case could be 1 for our example here. And that step response, if you actually look for that in the Laplace table, you actually see that the step response, being that immediate change in time, is characterized as 1 on S, where the 1 here actually maps the magnitude. So let's say if we had a step response that went from 0 to 12, the Laplace transform for that is going to be 12 on S. So yes, the main objective is get the outputs y of t in terms of the inputs x of t. So yeah, you mix up your terms a little bit. So y would be our outputs and x will be our inputs. And in solving for our step response, that basically means that the step response in terms of time, where we saw it's 0 for everything before time equals 0, and then 1 for everything time equal to 0 and forward in time, the Laplace transform that would be 1 on S. If our step response had a different magnitude, say that it went from 0 to like 12 or 0 to 14 and so forth, the Laplace transform is basically just going to be 12 on S or 14 on S. So the magnitude maps on the numerator here, and the denominator here will always be S for our transform accordingly for our step response. So because we now have our input here accordingly for our x of s, and we have our equation in terms of y of s here, we can actually do a lot of equation manipulation and then partial fraction it and so forth, and get it back in terms of y of t using the inverse Laplace transform. So as of such, we'll end up getting our Laplace transform from this form here, and do the inverse Laplace transform to get our y of t equation. Now, you might be asking, okay, what's this u of t signal here? But just remember, u of t here, when you watch it mathematically, this is just going to be 1 because we are concerned here for when time is more than or equal to 0, because we're dealing with a step response. So this equation, basically, if we need to put a time limit to characterize our equation a little bit more, we basically say this equation exists for t more than or equal to 0. And this is because we're dealing with a step response in particular. And just remember, the u of t signal here is basically just as a magnitude of 1. Because u of t was basically, I'm writing it here for you guys, 0 for time less than 0, and 1 for time more than or equal to 0. So if you actually graph out this y of t equation accordingly, we basically end up getting this nice plateauing curve, where we can see here there's an increase in our voltage for y of t until it reaches some sort of steady value. And in this case, our steady value would have been characterized by u of t, where the u of t had a magnitude of 1. But we also need to recall that the question at the start of this problem asks, okay, what's going to be the response time or the time taken for this actual circuit to hit our steady state value in particular. So that's why we have our x-axis here in terms of time. I need to write that in as well, so that way I can correct the slides. So in particular, we know that if we observe our graph here of a y of t signal, we know that we started with a 0 value, and from when time 0 go forward for our switch on, in this case, or when our circuit is switched on, our circuit basically ramps accordingly because of the behavior of the capacitor until it reaches some steady state value. And we can see basically it approximately is around 50 seconds in particular before we actually hit the steady state value for our equation. Why is the right hand side of the equation in square brackets? Oh, the square brackets are just there, just for a placeholder. They don't serve any purpose at all. We can just actually remove the square brackets. It's just there for aesthetic purposes. Right. Here. Basically, in answering the initial question for our problem, we now actually, from characterizing this y of t equation here and actually graphing it, we can see what's going to be our rise time here, or charge time for our capacitor, which is characterized by the y of t equation, which is basically the output voltage of the capacitor. And we can also see that we actually hit a steady state value accordingly for when the capacitor actually hits maximum charge. So in particular, if we characterize these two parts of the graph, the charge time here, or initial rise time here that we observe for this part of the graph, is what we refer to as our transient response of our system. So the transient response is basically our initial condition response of our system. The next part of the graph here is what we refer to as our steady state response, where we basically have no change in the signal whatsoever. So basically, for any typical system, you will always have an initial transient response once the circuit is switched on, and then a steady state response at which the system will be stable at. Now this holds true for stable systems. You'll see later on there's something known as an unstable system where this does not hold true, and we'll discuss that at length when we actually reach that point in our lectures. So just keep in mind, our initial conditions are what we refer to as our transient response. And once we hit a steady value, this is what we refer to as our steady state response. And these terms actually are going to come back a little bit later on as for how we evaluate the responses of our systems. So in observing the step response there, we saw that we obtained our transient response and our steady state response. But now actually, let's start looking at our impulse response. So we need to know, okay, what's going to be the response of our circuit for an impulse? And we know the input here is basically delta of t. If we actually try to evaluate the Laplace transform here, it comes like we have to do a little bit of tricky math. But thankfully, the Laplace transform table actually has the transform for this. But I'm just going to show you how it actually can be evaluated in the next few slides if you had to do it manually. So in particular, what happens here is that shifting property that we'll be observing in the last few lectures, that integral comes back and plays an important part for our shifting property. And as of such, the entire Laplace transform of any impulse will just resolve to 1. If there's a magnitude in front of the impulse, that means that the impulse here, when you Laplace transform, will just resolve to the magnitude accordingly as well. So as of such, in doing the Laplace transform of our impulse, in this case being our unit impulse, with a magnitude of 1, this means that we basically are going to sift out the value of the function at t equals 0, meaning that we just get a value of 1 accordingly because of the unit impulse. So basically, when we had our y of s equation here and our x of s equation, and our x of s term here on the right hand side, x of s now transforms to 1. So that means we just have y of s equal to our initial equation here. And because x of s is just 1, we just don't really bother to write it in. And we can do our equation manipulation and partial fractions and so forth, and then inverse Laplace transform to get our y of t equation here accordingly. If we actually plot this y of t equation, we basically see that it somewhat looks like a discharge curve instead. And basically we have a fall time here, representing our initial conditions as well. And then we have a steady state value where we actually have where the capacitor is totally discharged. And we can basically see that the time it takes for the capacitor to discharge is approximately around 60 seconds. I also need to include the axes here as well. Yeah, sure, I could go back to the Laplace of the Dirac function. Alright, so the Laplace of the Dirac function basically is that we just need to apply the shifting property that we observed in the last few lectures. So basically, once we actually apply this integral part here, from the zero negative to positive infinity, remember that the impulse here just exists at t equal to 0 for this entire integral range. So it comes like, when we actually apply the integral accordingly, it comes like we just have e of minus s of 0 when we actually evaluate this integral form. And this is particularly true because of the properties of the impulse, which was that delta of t was equal to 0, t not equal to 0, and then the area under the impulse was just basically 1. So that's why the entire integral here for this resolves in such that the limit is just substituted straight into e of minus s of t, and that limit here is just going to be at t equals 0. And as a result, we end up getting a value of 1, which basically represents the area under the impulse accordingly. And if you can recall, when we did the area under the impulse, it was basically just the integral form here, which is the same equation. The negative by the 0 basically represents the limit of the impulse. Basically, that's or we had, like in the previous lecture, we had an x2 negative and an x2 positive. It basically represents the previous transition before it steps up accordingly. So the 0 negative means that's when the signal was actually at 0. But if we watch for 0 positive, that's when our signal actually goes to 1. If it was t minus tau for the Dirac function, it will basically resolve to the same value because you're just finding the integral. What will happen here, on the other hand, is though, because now it's t minus tau, the tau value here basically represents where that impulse will just lie. But when you actually conduct the integral form here to actually find out what's the value, it will still be such that you substitute t equals 0 here accordingly, and you'll get a value of 1. And that's particularly true because of the integral range that we have here. Alright, we had any more further questions on this Laplace transform of the unit impulse? Yes, basically the time of the impulse is lost when you actually conduct the integral form here. And that's particularly true because of the range of the integration that we're observing. Alright, well, if we have any more questions, I'll just come back to the slide at this point in time. But let's move on for our actual graph. Right, so we basically see that when we actually evaluated the impulse response for our C circuit, this fall time here was about like 60 seconds. And we still had our initial transient response here that we observed in the previous step response graph, as well as we have a steady state value here accordingly for when we move on towards our final value with respect to our system, when the capacitor in this case is fully discharged. Okay, right. So in particular, when we actually observe the step response and the impulse response, you realize that the step response basically gives us an indicator of how our system will respond towards some positive steady state value. And our impulse response will be basically sort of the opposite in this case, but actually for us to see how our system can actually discharge accordingly from our initial condition. And in this particular case, remember that our step response basically was when the circuit was switched on. Our impulse response was basically like if we just turn on the system and then we just immediately turn it off. So in that case, we got like an immediate sharp transient, and then the system just discharged itself accordingly as of such. Alright, so actually that's the end of our lecture 5 at this point in time. And do we have any further questions regarding the content of this lecture before I move on towards lecture 6? Yes. The prolonged one would be the step response, because remember that is just if you just turn on the system and leave the switch on. And the acute one would be the impulse response, where it's like we just turn the system on and we immediately turn it off. Alright, yeah, sure. So basically, our step response, and I'll draw it out here for you, you need to understand why I'm saying this, is, so let's say our step response here, in terms of time, is that it just goes here, and then it just steps immediately to some actual value. In this case, we assume a unit step, so the value here is 1. So this comes like similarly to like if we just had a switch and before time equals 0 it was off, but then at time equals 0 going forward, it just goes on immediately. So it's like if we just turned on the switch for our entire system. However, our impulse response is basically this one signal here at time equals 0. But a magnitude here of 1 basically being our magnitude of our impulse, so to say. And this comes like before time equals 0 here, we basically say that the system is off. But this is like if we just turn on the switch and then we just turn it off immediately at this point in time. So as of such, the step response, as you saw in the previous slides, would have given us a nice rising curve, as we saw. So this basically means that we see how our system actually responds while it is kept on. So we have our nice rise equation here, indicating that we started from 0 and we approach some steady state value for the capacitor. So this is basically our capacitor is charging up, and this is when the capacitor hits maximum charge. So this is actually for the step response. But however, for the impulse response, because of this immediate change here, this becomes like, okay, the system is turned on immediately, and then we just turn it off. And then when we start observing from time equals to 0 go forward, it will have some initial charges because of the system was turned on. But then once the system is turned off here going forward with respect to time, the system basically just discharges itself. The system here being our output voltage of the capacitor. So that's why we have a discharge curve instead. And we can see here, basically, we had some initial value, yes, and then we approach some finite steady state value currently because of the discharge of the entire system. Right, nice. Alright, so I guess there probably aren't any further questions regarding the material of this lecture. But we have one more question. Will the impulse response curve be mirrored? Yes, you can say in this particular case it's mirrored, but remember we're dealing with a first order system here, where we only have like, we only have all our terms going up to the power of 1. What we're going to see later on when we start going to like a second order system, where we have the power of 2 involved, and when we go up in powers for polynomial systems, the responses here change in different behaviors. Yes, we do have a transient response and then we obtain a steady state response, but we won't get these nice smooth graphs that we're observing here. So it's technically not a mirror once you start increasing in the order of the system. It just looks like a mirror here because we're just dealing with an order of 1 for our systems right now. Right, any more further questions? Typically, if you're doing like a full graph, yes, you will show both. But the reason that they're separated is to show the difference of the responses in particular. But yes, well, from the time you turn it on, there will be some charging, and then when you actually turn it off, there will be a discharge accordingly. But if it just remains on, it will just hit the steady state value and just stay at the steady state value. Alright, okay, so let's move on to the next lecture in the meantime. Saved, so I'll make that corrections accordingly. Okay, so the last lecture for today in particular is what we're going to focus on is system characteristics. And in particular, we'll be focusing on 4 characteristics as to how we actually can define our systems. And we'll observe each one in turn in this lecture and how we actually can apply them to our mathematical equations to determine how do we actually characterize our systems accordingly. Oh, whoops, there actually are 5 properties. Okay, yes, so we were observing these 5 properties in particular. So the 5 properties that we're going to be observing in turn are going to be causality, memory, time invariance, linearity, and a bounded input, bounded output. Now, most of these are very straightforward. They are like 1 of 2 that you actually need to pay a little bit of attention to. But when we reach those parts, I'll go into a little more detail as of such and explain it a little bit further. So our first property we're going to observe is causality. And causality actually is probably a really easy one to memorize. What this basically means is that we're saying here a system is causal if the output doesn't anticipate future values of the input. This basically says that once the output of any time depends on the value of the input up to that time, we're not dependent on future values. So as of such, once we have our initial time here and then we're dependent on past values, we're okay. But if we depend on future values in time, then our system is no longer causal. So in particular, let's actually watch this for some of our equations. So our first equation here, we can see that we have a delayed signal here of t minus 1. And that means that because we have a delay signal here, we're going to be watching in particular, since that y of 5 here, if we say t is equal to 5, is going to depend on x of 4. And x of 4 occurred before y of 5. Because we're watching in terms of what's in the brackets here. So on the right hand side, we're watching at the time instance of 5. But on the left hand side here, we're watching at the time instance of 4. And because the time instance of 4 is in the past, and when compared to the time instance of 5, we actually say in this case that our system here is causal. The u of t signal here, if you ever see it, remember this is just the unit step. So this means that we are observing the signal accordingly for t more than equal to 0. Need to put that in as well. Correction. So this would be for t more than equal to 0. However, let's say if the right hand side of the equation here, which maps our inputs, depends on a future value of a time instance. So let's say t here was equal to 5 on the output side here, being our y of t. But our input side here, because the time instance here is going to be 6, because it's t plus 1, this is actually a future value in time. So as of such, because it depends on a future value in time accordingly, the system here is non-causal. And our last example here, this is actually something you need to pay attention to once we actually start inverting the signs here for t or n accordingly. So we can say basically that if we said n was equal to 5, and this will actually depend on x minus 5, need to correct that as well. So because we're dependent here on a previous value of our input to get our current value of our output, because on this side here it's going to be 5, but on the right hand side here, sorry, it's going to be minus 5. This system actually appears to be causal, and this actually will hold true for n more than equal to 0. But however, if we invert the opposite, so we say n here is negative 5, this then means that x here is going to be positive 5 accordingly. And that means it actually will start depending on a future value. As of such, the entire system is non-causal unless n here is positive. So the trick to causality in particular is that you need to make sure that your outputs will always depend on past values or current values of the inputs. Once your output depends on future values of the input, your system is non-causal. And in order to observe if it's going to be a past, current, or future value, you need to observe what the time instant is going to be here on the output, as well as the time instance on the input as well. That's basically causality for how determining if a system is causal or non-causal. Are there any particular questions regarding causality at this point in time? Right, yeah, sure. So this one here in particular, we were watching when n was equal to 5. So on the on the left hand side here, this would be an instance of n equals 5. But on the right hand side here, because we have minus n, this is actually going to be an instance of minus 5. So this actually appears that minus 5 occurs before positive 5, so it actually looks like the system is causal, because the output here is in the future, but the input here is in the past. However, if we say n was equal to minus 5 here, that means y of minus 5, meaning a previous value, or a previous time instance. If we put minus 5 here for n, that's minus minus 5, so that gives us positive 5. In that case, our input here is going to be at the time instance of 5, or the n instance of 5 in this case, and this is going to be a future value. So in this particular case, where the instance here is negative 5 on the output, but the instance on the input is positive 5, depending on the future value of the input, the system will be non-causal. So, however, so long as n remains positive, on the other hand, the system actually is causal. So if we said n was equal to 0, like in particular, that means that it will actually be at the same value accordingly, because it will be y of 0 and x of 0. An example of a non-causal system would be something similar to that of if you can predict the future in particular. So like, if you're doing some sort of prediction software, or you're trying to predict trends to see if it actually matches, because you're going to be trying to basically get an idea of what the input values are going to be like within the future, which don't exist as yet. So we can say basically like if it's going to be something like a forecasting application, or if you're thinking about like the stock market in particular, what's going to be the trend if the stock is going to rise or fall based on the values that you have. And then because you're going to be predicting this, any future values that you'll be using in particular, that it's going to determine the future values of trends in particular as you keep on going. So a non-causal system is basically anything to do with prediction or forecasting in particular. Non-causal systems cannot exist in nature. They are solely man-made. And for anyone who wants to be like, well, okay, we have things like psychics who can predict the future, whatnot and so forth, that's a little bit of an anomaly and speculative. But for our purposes, non-causal systems cannot exist in nature. They will solely be man-made. Alright, so let's go on to the next property in particular. Oh, sorry, yeah, so I had an explanation here. So basically, causality signals are basically real-time physical signals. They only exist in the real world. And basically, if you could start predicting the future, especially for the stock market, you will be making a lot of money. Because then you'll know, okay, if the price is going to rise beforehand, if the price is going to fall, and you'll know whether to buy or sell your stocks accordingly. One thing to note in particular is that causality cannot apply to spatially varying signals. It can move both left and right and up and down accordingly, but once you have signals that basically sort of jump all over the place, in this particular case, or piecewise continuous signals, we cannot apply causality to these signals. And causality does not apply also to systems processing recording signals. So a recorded video in particular, it's basically that you can go forward and backward in time because it's basically has been recorded at this point in time. But it's similar to that saying that we know a recorded video starts at time equals 0, so there's nothing like time negative. Versus a live broadcast where the time just only moves forward, you can never go back. So causality applies in different ways, but the simplest explanation, as said in the chat, is basically for real world signals, you're basically dealing with causal signals, and once it's man-made signals or recorded signals, you'll be dealing with non-causal signals accordingly. Alright, so our next property here is basically going to be memory, and the term memory basically implies some sort of storage. Because we will be watching this for a causal system, any causal system will always be memoryless or static, and it will depend only on this condition here, where at any time t1, the value of the output at t1 depends only on the value of the input at t1. So that means that the inputs and outputs must be at the same time instance for it to be memoryless or static. However, once it depends on past values, this means that these values need to be stored. So if the output depends on past values of the inputs, being these past values being past time instances, that means these values need to be stored somewhere in memory. As such, our causal system will have memory. With physical components, this means that we no longer be storing some sort of charge. So if you have a fully resistive system, meaning that you only have resistances, that basically means it doesn't store any charge whatsoever in that system. So that's a totally memoryless system. But however, once you have things like capacitors and inductors and anything that stores some sort of charge, that means your system now has memory within it. So a typical example would be our resistance capacitor circuit. And we know that a capacitor here basically stores charge. So this capacitor here acts as memory in particular. And that's because it depends on the past events, being the past inputs of x of t, and then it will depend on the output here, being y of t accordingly. And we know from our integral equation for this, once we have that integration sign inside there, that means there's memory involved. So in particular, a memoryless system just literally does not have any energy storage components. There will be no derivatives, no integrals, and no delays in the system equation. But once you have any one of these here, the system contains memory. So the short version is, once your outputs depend on past values in the inputs, that means you will have memory in your system. But once you are at the same time instance on both output and input, if you're dependent on future values, that means you have no memory within your system accordingly. The difference between causal and having memory is such that they typically go hand in hand in particular, but you can have a causal system at the same time instance on input and output. A memory system would be where the outputs will only depend on past values of the inputs accordingly. But once the output and input are at the same time instance, it's basically memoryless. A causal system, on the other hand, can exist at the same time instances for both the input and the output, as well as once the output depends on past values of the input. Right. So, are there any further questions regarding the memory characteristic? Yeah, sure. So, I'll give you an idea what it means. So, for causality, we basically know that the outputs here and the inputs here, let's say if the output here was at 5, yes, it's possible for a causal system to have memory and vice versa. And let's say the input here was at 5, so let's say this was our 5 instance. So because we're at the same time instance here, this is a causal system. So this is causal. But however, because we're at the same time instance, it does not depend on any past values of the inputs. So we don't have to store any values accordingly. And because we don't store any past values from the inputs, that means we don't need any memory. Now let's actually watch, let's say when the output here was at time instance 5, or input here was at like say time instance 2. That means, yes, our system is still causal. But because we're depending on past values here on the inputs to get our outputs, that means we need to store these values accordingly somewhere. And because we need to store these values, that means our system has some sort of memory. So once you have to depend on past values in your input to get your current output value, you will always have memory. If you are at the same time instance, or if you are dependent on future time instances, there will be no memory involved. And we saw in the previous slides that a causal system, for any system to be causal, it needs to be either at the same time instance for both output and input, or that the output depends on a past value or past time instance value of the inputs. So for a system to be causal and have memory, just to recap, that means the time instance at the output, when mapped to the time instance of the inputs, the input time instance must be less than the output time instance. However, once the input time instance matches that of the output time instance, or is greater than that of the output time instance, your system will now be memoryless. In the event that if the output time instance is less than the input time instance, that now means your system is non-causal and memoryless. So that's like the third condition here if I write it down for you. So that would be like if our output here was 5 and the input here was like 7, this would be non-causal and memoryless. The derivatives, integrals, and the equations can actually be used to model memory components, yes. We don't really go much into detail about how this is actually modeled, but you get like an idea later on in further lectures how this actually can be done. So are there any more rectifications to be made with regards to the differences between the causal and memory properties? Well, just to give you an idea, because we're talking about it with less than and more than and whatnot and so what. This one is equal to, this one is less than, this one is more than. Oh, whoops, I actually wrote that the wrong way. This one is more than, this one is less than. Alright, that's more sensible. So yeah, once you watch actually that table I dropped there, you can determine if a system is causal and has memory, or if it's non-causal and if it's going to be memoryless, and so forth, just by watching those three properties on the tables. So equal to, meaning if they're at the same time instance, it's causal and memoryless. If the output is more than the input in time instance, that means that's causal and memory. If the output is less than the input in time instance, that means it's going to be non-causal and memoryless. Alright, any further questions regarding this at this point in time? Alright, looks like we have no further questions at this point in time, so we're moving on to the next property in particular. Alright, so our next property here is time invariance. And basically what this means is that if we have any time shifts accordingly, the time shifts need to be directly mapped from the inputs and outputs. As such, once any occurrence of the output changes by delta of t, that needs to be mapped to the same occurrence of change on the input side as well. As such, if we change our inputs such that instead of being the t, it needs to be t minus tau, it needs to be directly mapped to our output here as well for t minus tau. Similarly, in discretized time, our shift there will be n minus m, and that same mapping must be observed for time invariance. If this mapping cannot be observed, the system is going to be time variance. But so long as you can prove a direct mapping for this time shift, your system will be time invariant. And we'll watch a few examples on the next slide here in particular. So if we had y of t here maps to txt plus 4, and we apply our time shift here, basically we can see as such, we can have y of t minus tau here on the left hand side. Correct that. Oh, whoops. No, I actually had it on the equations. Okay. Don't need to put that in. Alright, yeah. So we can basically see that once we substitute in t minus tau here on the right hand side of the equation, it comes like we had tx of t minus tau here plus 4. And as of such, we can't map this back directly to y of t minus tau. This t variable here will also change such that it will be t minus tau accordingly as well. So that's the correction I need to make on this slide. So if we had that mapping there for t, we have been okay. But because we're watching the mapping only for x of t in particular, that means that this mapping here for t does not exist. And as such, we can't prove a direct mapping for y of t minus tau, because we only observe the substitution here for x of t. We're not observing the substitution here for t, we are observing it for x of t only. If we observe the substitution for t, that means this t here would have been t minus tau, and then we could have proved a direct mapping for y of t minus tau. But because we can't prove this, because we just want to substitute x of t here equal to x of t minus tau, our system here is time variant. If we watch our second example here, we have y of nt equal to x squared of nt. And if we map this accordingly, where we substitute x of nt only to be x of n minus m of t, we can see here that on the right hand side of our equation, we will have x squared of n minus mt. And if we substituted y of nt here to be y of n minus mt, we have obtained the same equation here accordingly. So once we are able to obtain the same equation, we can then say our system here is time invariant. So the steps for proving time invariance or time variance accordingly is that we start with our input equation here, being that y of t is equal to some sort of form equation here, or y of nt equals to some form, and then we only substitute for wherever x of t is to be x of t minus tau. In obtaining the resultant equation here, we then see what happens if we actually substitute the entire t here as t minus tau instead, and we obtain back the same equation. If we are able to obtain the same equation, our system is time invariant. But if we cannot obtain the same equation, our system now becomes time variant. So are there any particular questions for time invariance? Yeah, sure, I can go over one more time. Actually, I'll write it out for you guys, so actually you can see what I'm talking about here. So, let's start with this equation in particular. Alright, so our first thing would be to substitute x of t here is equal to x of t minus tau. So, as such, when we do the substitution, we get t of x t minus tau plus 4. Our next step would be to substitute t is equal to t minus tau for y of t. So that means we get y of t minus tau is now equal to t minus tau of x t minus tau plus 4. This equation here does not map to this equation. because the mapping does not exist, that means we end up with a time variant thing, the time variant property. Let be x squared nt equal to x squared n minus nt. Alright, I'll do the second one so I can answer that question in particular as well. So for this one, what we first do is that we watch only the right hand side of the S equation here. So we observe this here, and then we do this substitution. RHS being right hand side of the equation. So as of such, for the right hand side, we'll get x squared of n minus m t. And then our next step was supposed to be if we substitute this case nt equal to n minus m t for y of nt. So as of such, y of n minus m t will now be the same as if we did that previous substitution. And because this is basically the same as we saw with this one, that's how we get to prove that it's time invariance. Hopefully that answers the x squared nt question that was asked in the chat. And so basically for time invariance, you need to be able to change t on both sides by the same value. Yes, that's basically what you need to observe. But the first thing is that the first step is that you substitute the x of t equal to x of t minus tau. Or in the discretized form, it will be x of n minus mt. And you only do that for wherever x of t is or wherever x of nt is. You don't care about the y of t or the y of nt in that first instance. So you get the resultant equation there. And that's what's going to be what you're going to be comparing to when you actually substitute t in this case being equal to t minus tau. Or for a discretized version, when nt is equal to n minus m of t. And if you are able to obtain the same equation when you do these substitutions, you then prove that your system is time invariant. If you are unable to get the same equations, in this particular case for our first equation, y of t equal to tx of t plus 4, your system is then time variant. So you must have the initial equation for when you substitute x of t equals to x of t minus tau. So that will be the initial equation. That's what you're guessing when you do the substitution. And then this equation that you need to compare to is when you actually do the substitution for t equal to t minus tau here accordingly. And if you get the same equations, you basically prove that your system is time variant. If you cannot get the same equations, no, you prove that your system is time invariant. If you cannot get the same equations, you prove that your system is time variant. So yes, a person in the chat is basically giving you guys the steps as to how to basically do it. Once you compare the results of steps 1 and 2, once they're equivalent, it's time invariant. If they do not match, it is time variant. Right. Any further questions on time invariance at this point? Okay, so one more question. So the time invariance in the first equation is caused because the first t on the right hand side does correspond to the second equation. Okay, I think what you meant to ask was the time variance in the first equation is caused because the first t on the right hand side does not correspond to the second equation. So yes, that's how you prove time variance. Yes, yeah. So yeah, your time variance in the first equation is caused because the first t on the right hand side does not correspond to the second equation when you did that substitution. But once it's the same equation that you obtain, you prove that your system is time invariant. So yes. Alright, so let's move on to the next part in particular. If there are any further questions, I'll go back towards it. Right. So our next property that we need to observe is linearity. So in particular, once you can prove that your system is linear, you need to just check the principle of superposition for any combination of inputs. So basically what this means here, once your x1s map to your y1s and your x2s map to the y2, once x here is equal to some scalar multiplied by x1 and x2 accordingly, and your scalars here being a and b, you can prove that the mapping from between x and y is basically going to be the same as if we just change x here to y. So as long as you have a single t alone by themselves, yes, if you have a single t alone by itself, the system will be time invariant. Not time variance, time invariance. No, sorry. Okay, I understand what you're asking. If it's x of t by itself, I mean if the t is in the brackets, the system will be time invariant. But once you have a single t variable existing outside of the brackets, yes, your system will be time variant. Yes, that's true. Alright. So for linearity, basically what this means is that once you have your mapping between x1 and y1 and x2 and y2, if you apply the addition of the two signals multiplied by any scalars, being a and b here, once you can prove this mapping exists between x and y, you can actually prove that your system is linear. And what this basically means is that once you have a system of order 1 in particular, meaning that you have no squares or cubes and so forth and whatnot, your system is basically going to be linear. Once you start going off in increasing orders of your system, that means your system is non-linear. So let's watch a couple examples here in particular. So for our first equation here, if we have y of t is equal to 3x of t, we substitute x of t here to be ax1t plus bx2 of t, we basically can see that when we do the substitution, we get 3ax1 of t plus 3bx2 of t. And if we watch our mapping here accordingly, this comes like if 3ax1 of t here can directly map to ay1 of t, because x1 and y1 can be directly mapped accordingly. And 3bx2 of t here can be mapped directly to y2 of t accordingly. So once you can prove that the mappings exist for each one of these components, and you obtain a similar form of equation accordingly, you can prove that your system is linear. However, if this was a squared term here, and of course it's a lot more common sense once you see anything being squared or cubed, you obviously know it's not non-linear. When you try to mathematically prove this using your substitution for x of t, you can see that you're going to get a whole set of weird components once you start expanding out here. And you cannot map this back to a y1 of t plus b y2 of t. As such, your system will be non-linear. So the simplest way to determine if your system is linear or not, the order of the system must be 1. Meaning that all your x components here, all your y components, all your z components, whatever is going to be on the input side of the equation or the right hand side of the equation, once it maps back to y of t here, it needs to be here of order 1. It cannot be squared, it cannot be cubed, it cannot be negative powers, it can't be any of those things. It must map to order 1. Once you have an order that is greater than or less than 1, your system is basically going to be non-linear. So once you have a square term, a cube term, a square root term, something to the power of -1, -2, and so forth, your system is no longer linear. It is a non-linear equation. The proof here is basically to give you an idea of how you actually can go about proving linearity itself. By showing that if you did the substitutions here, you can do a direct mapping between the x1 and y1 and x2 and y2 accordingly. So if we watch here for a purely resistive system, and we know that our y of t equation here can be mapped to get in terms of x of t, but basically we'll be observing the voltage across one of these resistances. If we do our substitution here for x of t and we plug it into the equation here, and then we remap the equation accordingly, we can basically get a mapping in between x1 to y1 and x2 to y2, where r1 divided by r1 plus r2 can be mapped straight to our next a component here, because this is just going to be a scalar value. And br1 divided by r1 plus r2 here can be mapped to the next b component here, which is basically just going to be a scalar value. So this is how you actually prove if your system is linear. So yes, if your power is 0, in that case, you just get a value of 1. So yeah, it's just linear. So yes, for a purely resistive system, your system is basically going to be linear. However, let's say we introduce a diode into your system here. This diode now makes your system into a piecewise continuous equation. If you do a general substitution here, so let's say if xt was equal to the unit step, it basically looks like it's still linear, but that's only for the first half of the equation. When you actually start observing it a little bit more, let's say if we let x of t be a reverse unit step in particular, when you actually watch this substitution here, the reverse unit step, it cannot be equal to 0. That means for everything before time equals 0, it's going to be 1. And that means it's going to exist. And this, when you watch it, it does not map to negative y of t. As such, when you do this mathematical proof here, and you can't obtain back your mapping for y of t, this proves that your system here is non-linear. So, a truly resistive system will always be linear. But once you have any other components besides resistors within your circuit, be it diodes, capacitors, inductors, and so forth, your system is no longer linear. So, plenty systems that exist in the real world are basically non-linear systems, because they depend on like a host of the different circuit elements, and typically most systems are never so simple. In the real world, you'll always be dealing with higher order systems, so it's very rare to encounter a linear system for real-world systems. However, for the purpose of this course, we will be focusing exclusively on linear systems only. And in particular, the reason for this being is that even if when you do have a non-linear system, in order to analyze it, you actually approximate the non-linearity of those systems into linear sections in particular to observe the behavior at particular points in time. So in doing this linear approximation for non-linear systems, it becomes possible for you to actually characterize the system in some form or fashion. And this only works in particular for certain points in time when you can actually do this approximation. Alright, yeah, I'll go back to the diode example in particular. So the diode example basically means that once we have this diode in the system here, we can basically characterize our equation here now in terms of a piecewise equation. So this is all going to be a piecewise continuous function because of the diode that is included here. The diode basically means that the current in the system can only flow in one direction. It cannot go backwards. The diode will just basically make sure that the current cannot go in the opposite direction. So because of that, that means once your system is switched on, being for x of t being more than or equal to 0, we still have our same equation accordingly. But if it's that the current decided to flow in the reverse direction, for x of t being less than 0, that means this diode here would stop any current from being transmitted within the system. So as of such, your output voltage or your output value here is going to be 0. Now, a simple way to actually prove this, because we have x of t here as our limit on our right hand side of the equation, is that let's take the unit step and see if we can map it back to y of t accordingly. So first we start with the positive unit step, saying x of t is equal to u of t. So if we did the substitution here accordingly, we can basically see that we get a similar mapping to that of y of t here. And because for t less than 0, that means that the u of t here will just be 0. That means we will also get back y of t here is equal to 0 accordingly. So it looks like it's linear for this point in time. But when we use a normal unit step. However, the proof must also exist if we actually change the sign of the unit step in front of it, i.e. if we reverse the unit step. So the first instance is where we had u of t, and we were able to prove that the linearity exists for the equation. But linearity also needs to exist for all values of u of t accordingly, be it that if there's the sign is positive in the front here, or if the sign is negative. So when we substitute negative u of t here into our equation, and we actually observe the values here, we can see here for negative u of t, what happens is that in this case, because of the diode here, that does not want to let the current flow in the reverse direction. As such, because of that diode component, you'll end up getting 0 accordingly. So remember, this only allows for current to flow in one direction, being the forward direction. If we had a negative unit step, it comes like if we are allowing current to flow in the reverse direction. And because this is equal to 0, this definitely is not going to be equal to negative y of t because of the mapping. As of such, you end up getting non-linearity for your system. You cannot prove that you obtain negative y of t here accordingly. So yes, linearity must hold for piecewise functions. Once you have for each piece, it must hold for every single piece. And yes, piecewise functions represent an easier way to compact multiple interval test cases in that particular case. Yes. Linear systems must exist for all values of t. It cannot just only be for positive values of t. It must exist for negative values of t as well. That's why we tested for negative u of t in this particular case, to see if the linearity exists as well. Right. So yeah, I was explaining this before I went back to those slides. We'll be focusing only exclusively on linear systems. And it's because we'll be doing, for any nonlinear characteristics that we observe, we'll be approximating them to linear characteristics in order to do our signal analysis and signal processing accordingly throughout the entire course. Right. So, are there any further questions on linear systems at this point in time? So if you had a piecewise system with two different linear parts, but due to them being different with the overall system, we consider nonlinear. It will depend on each one of the pieces, actually. So if you can prove that for each one of the pieces that linearity does exist, then you can consider the system being linear overall. But if you're thinking about the system being nonlinear because of if there's any discontinuities or any jumps in the signal, you can say yes, it can be considered nonlinear because of those jumps in the entire system. But then you can say for each piece of the system, it's still linear accordingly. So it depends on the case that how you tend to deal with it. And in particular, most people would say, yes, the entire system is non-linear, but the majority of the system is linear. And that would basically just only be due because of the discontinuity effect within the system. However, if the discontinuity doesn't exist, let's say if the signals do join themselves together, and a good example of this would be like a triangular wave. So it's like if we had triangular wave here, and this touch at the same point here, you can basically make an argument to say that the entire system is linear. But it's still similar to that if you have a discontinuity at this point here in particular. So for our argument's sake, we will say that the entire system is non-linear, but for each part of the system, it will be linear. Alright. So I think this would be the last property that we'll be discussing in particular, and the last property will be bounded systems. If it's not the last property, the next property might be something with linear time invariance or something like that, but we'll get to it. Yeah. Right. So for a bounded system, this actually is probably really simple. A bounded system means that the amplitude is always known. There are no asymptotes present within the system. So you have no, let me see if I could draw this for you. Comes like, if we have something like this going towards infinity, and then something like this going towards infinity and whatnot, that's an unbounded system. Once the amplitude is known and it is finite, your system is bounded. So in particular, any system that you tend to deal with and you want to characterize it as bounded input, bounded output, or known as BIBO, is that once you know that your amplitudes remain finite accordingly, you will always have a Bibo stability system. So yeah, once you have no asymptotes present within your system, meaning that there's no values tending towards infinity and so forth, your system is basically a bounded system. Once you do have asymptotes, on the other hand, your system is basically unbounded. Actually, no, a discontinuity will not be considered as an asymptote, because it just means that you still know what the amplitude is at that point in time, and then it just jumps towards another amplitude at that point. The reason for why I say an asymptote in particular is that the values tend towards infinity. So we still know what the amplitude is for a discontinuity, because we can physically see what the value is. But the asymptotes in particular just means that the values do not have a finite value. They just go straight towards infinity. So in particular, this course and the entirety of this course will be focusing on Bibo linear time invariant systems. We will not be focusing anything outside of these properties. Bounded input, output systems, meaning that the amplitude will always be known. We will be focusing exclusively on linear systems, or approximations of nonlinears to nonlinear systems. So we're only doing analysis on linear sections, and time invariant systems, where that we will have only such that when we're watching the time invariance and so forth, that we'll have a direct mapping if the time shifts accordingly between input and output. And the main reason for this is that Bibo linear time invariant systems are probably the more simplest way, I can't say simple, the more simpler way to actually observe signal and systems characteristics in particular. And those four signals that we saw that are useful for analyzing the signal and system characteristics, being our step, impulse, and sinusoid signals and our ramp signals, it actually helps us if we have our system characterized at this particular characteristic, being Bibo linear time invariant. It becomes very possible to predict the response of the system to other types of inputs in particular, making our analysis quite easier to conduct. Alright, so that's the end of lecture 6, and if there are any further questions at this point in time, please ask them. Alright, so it looks like we don't have any further questions at this point in time. So next week in particular, we'll be actually doing problem set 1, and I'll upload problem set 1 onto myELearning. For anybody who you know that still doesn't have access to myELearning, please ensure that they do get a copy of it once it's uploaded via some form of communication means and whatnot. And next week in particular, the lectures that we were going to be focusing on would be the Laplace transform review, poles and zeros, and the initial and final value theorem. And in particular, the initial and final value theorem will be going hand in hand with the Laplace transform. But actually, how do we analyze the transient response and the steady state response of systems in which we observed today in today's lectures in particular? Fours and zeros will also go hand in hand for us to determine the stability of our systems and whatnot. So we'll be looking at those in particular for next week. And like I said, I will put up problem set 1, and I will also like for you guys to actually attempt problem set 1 because we have covered enough material at this point in time. And I'll also put up a vote for us to do 3 questions for problem set 1 that gave you guys the most trouble, because we literally wouldn't have all the time in the world to do all the questions. I will post up the solution afterwards that session for you guys to observe them, but any questions in particular that gave you the most trouble, I'll actually work them out on the screen here in particular for you guys to see actually how to approach them and so forth. Right, I have 1 question to go over time invariance, so I will go that over before I end. Alright, so time invariant operates. Excuse me, 1 second. Alright, sorry about that. Okay, so yeah, thanks. The problem set will be posted either by the end of today or tomorrow morning. I'm trying to post it today. Alright, so in going over time invariant, for the person who asked this in the chat, time invariant operates on 3 steps. And one of your colleagues actually posts the steps in the chat. So step 1 would be to apply the mapping of x of t such that x of t alone is equal to x of t minus tau into the equation. You will get a resultant equation here, which will be serving as if it's going to be the comparison for when you do the next step. Step 2 would be to transform all the t variables in the entire equation to t minus tau. And then once you get the resultant equation here, your final step will be to compare the results of step 1 and step 2. If they are equivalent, your transfer function here that you're observing for y of t and x of t is going to be time invariant. If they do not match, it is going to be time variant, sorry. So I'll erase one of these to redo it as a physical example. I'll post up the problem set either by the end of today or tomorrow morning for the latest, once myELearning is loading properly and whatnot, because I was trying to post it up before today's class, but it was taking ages to load. Alright. So step 1 is substitute x of t only is equal to x of t minus tau, which results us and we're watching for this equation. We'll get tx of t minus tau plus 4. Step 2 will be to substitute t equals to t minus tau, which means that we will get t minus tau of x, t minus tau plus 4. Step 3 is to compare. And we will compare in steps 1 and 2. If equal, they are time invariant. To write that in proper English. System is time invariant. If not, time variant. So those basically are the 3 steps that you'll be doing to prove if a system is time invariant or not. So hopefully that helps with the explanation as to how you actually do this accordingly. Alright, nice. Right, so just recapping what I said for next week, I will post up problem set 1 either by later today or tomorrow once myELearning is behaving itself. I can actually upload it. For people who don't have access to myELearning, please ensure that you circulate the problem set towards them via any other communication means. And the lectures in particular where we're observing for next week would be the Laplace transform review, the poles and zeros lecture, and the initial and final value theorem. In particular, the Laplace transform goes hand in hand with the initial and final value theorem to evaluate the transient response and the steady state response of systems. And poles and zeros in particular will determine if a system is stable or not. So we're looking at those in particular as well. For the problem set, I'd like for you guys to actually attempt those questions over the course of the week. And I will post up a choice question on myELearning for you guys to vote on which questions gave you the most problems, and the 3 highest ranked questions, we will actually do those next week, Tuesday, during the tutorial session. Because there isn't enough time to do all the questions in particular. Once we're finished with that session, I will post up the solutions for all the questions, and if there's anything else that requires some clarification, you guys can actually email me accordingly, and I actually can explain to you how to do some of those workings in particular. So, until then, take care, be safe, and I'll see you guys next week. So, that's it for now, and make sure you guys are okay for the rest of the week.